In July of 2025, the James Webb Space Telescope spotted something that had no business being where it was. Between two colliding galaxies, floating in the void between them, was a supermassive black hole. It did not belong to either galaxy. Both of those already had their own central black holes. This third one was simply there in open space, unexplained. No stellar remnant, no obvious origin, just a black hole sitting between galaxies, as if it had materialized from the gas and dust of the early cosmos directly, bypassing every step we assumed was required to build one. That single observation quietly shook the foundations of how we thought black holes were made, and it was not the only one. Over the past few years, a wave of new discoveries has forced astronomers to revisit some of the most basic assumptions in astrophysics. Not because our models are completely wrong, but because the universe keeps filling in details we had not anticipated. Black holes, it turns out, come in more varieties, form through more pathways, and behave in more extreme ways than the textbooks suggested even a decade ago. To understand why any of this matters, it helps to go back to what we thought we knew. For most of the 20th century, there was essentially one accepted recipe for building a black hole. You start with a very massive star, at least 20 times the mass of our sun. That star burns through its nuclear fuel over millions of years, and when the fuel runs out, the star explodes in a supernova. The outer layers scatter into space, and the core collapses inward under its own gravity. If the remaining mass is large enough, the collapse does not stop. It keeps going until the density exceeds a critical threshold, the point at which not even light has enough velocity to escape the gravitational pull. The result is a stellar black hole. Stars smaller than about 20 solar masses still go supernova, but the collapse is not quite powerful enough to push past the threshold. Instead, they leave behind neutron stars, which are extraordinarily dense objects made almost entirely of tightly packed neutrons, but which are not black holes. And stars smaller than roughly 8 solar masses do not go supernova at all. They shed their outer layers gradually and leave behind a white dwarf. So the model imposed limits in both directions. Stellar black holes could not be born much smaller than a few times the mass of the sun, because the collapsing core needed a minimum mass to cross the threshold. And they could not be born much larger than the most massive stars, which cap out at a few hundred solar masses. Below a certain floor, no black hole. Above a certain ceiling, still no black hole. That was the model. Then we looked further out into the universe and found both. The first surprise was the discovery that the cores of large galaxies harbor black holes with masses ranging from hundreds of thousands to tens of billions of times that of our sun. These are supermassive black holes, and they are in a completely different league from stellar black holes. The first quasar, a brilliantly luminous galactic center, was identified in 1963. By 1971, the first theoretical predictions of a massive black hole at the center of a galaxy had been published. Over the following decades, evidence mounted that supermassive black holes were not rare exceptions, but a standard feature of large galaxies, including our own. Our galaxy's central black hole is called Sagittarius A star. It contains about 4 million solar masses. It is currently quiet because its accretion disk is thin and faint, but it is unambiguously a supermassive black hole sitting at the center of the Milky Way. The question that followed was obvious. How did these things form? The straightforward answer would be that stellar black holes accumulate mass over billions of years, growing step by step from a few solar masses to millions or billions. That is theoretically possible. But a problem emerged when the James Webb Space Telescope began returning images of the very early universe. Webb was designed to observe light from the first few 100 million years after the Big Bang, and it delivered. What it showed was a universe that was already far more developed than expected. There were galaxies. There were supermassive black holes inside those galaxies, and some of those black holes existed when the universe was only about 500 million years old. That is not enough time for a stellar black hole to grow into a supermassive one by conventional feeding. Even at maximum possible accretion rates, the math does not work without some extraordinary assumptions. This is where the Eddington limit becomes central to the problem. In 1920, The English astrophysicist Arthur Eddington worked out that there is a fundamental cap on how quickly a star, or later a black hole's accretion disk, can radiate energy while still pulling in new matter. The mechanism is straightforward. When matter falls toward a black hole, friction in the surrounding accretion disk converts gravitational energy into heat and light. Those photons stream outward. But photons carry momentum, and that outward pressure pushes back against infalling matter. Above a certain luminosity, the radiation pressure overcomes gravity entirely, and the black hole effectively blows away its own food supply. This limit, the Eddington limit, means black holes cannot simply eat as fast as they want. The brighter the accretion disk, the more resistant it becomes to further feeding. Growing a stellar black hole into a supermassive one by 500 million years after the Big Bang would require that black hole to feed continuously at or near the Eddington limit from the moment of its formation. Simulations confirm this is technically possible, but highly unlikely. Black holes in reality periodically run out of nearby matter and must wait. They are not always eating. This mismatch led many researchers to propose an alternative origin story. Maybe supermassive black holes did not grow up from stellar black holes at all. Maybe they were born supermassive, or close to it, through a completely different mechanism. The idea is called direct collapse. In the very early universe, when everything was much more compressed and dense, conditions may have allowed massive clouds of interstellar gas to collapse directly into black holes without ever forming stars first. No supernova required. No intermediate stellar phase, just gas, gravity, and collapse. If that happened, a black hole could begin its life already carrying a mass of 100,000 solar masses or more, giving it a massive head start on the growth that follows. This idea had long been theoretical. Evidence was sparse. Then James Webb started finding things that fit. The isolated supermassive black hole discovered in July 2025, floating between two colliding galaxies, was one piece of evidence. The researchers who found it concluded it most likely formed through the direct collapse of a gas cloud in the space between the galaxies, not from any stellar process. It had not been ejected. It had simply formed there. A second piece came from a black hole called QSO-1, also discovered by Webb. QSO-1 sits inside a surprisingly small galaxy with an unusual chemical signature. Spectral analysis showed that the galaxy contains less than 1% of the oxygen found in the Milky Way. Heavy elements, everything beyond hydrogen and helium, are produced by stars over successive generations. A galaxy with almost no oxygen is a galaxy where very little stellar activity has occurred. If stellar processes had not yet had time to produce heavy elements, then the supermassive black hole at its center could not have grown from stellar remnants. It had to have come from somewhere else. Neither observation is a definitive proof on its own, but taken together, they make the case that direct collapse black holes are real, that the early universe could and did produce black holes outside the stellar pathway. And if that is true for massive black holes, the same logic extends downward in scale. Here is where the story takes a different turn. If the early universe could produce black holes through direct collapse at large scales, could it also have produced much smaller ones? The answer, proposed in 1966 by the Soviet physicists Yakov Zeldovich and Igor Novikov, is yes. These are called primordial black holes. The idea is rooted in the physics of the very first fraction of a second after the Big Bang. In those earliest moments, the universe was an extraordinarily hot, dense plasma. Matter was not distributed with perfect uniformity. There were regions of higher density and regions of lower density, statistical fluctuations in the distribution of particles. In areas where density exceeded a critical threshold, gravity could have won out against the outward pressure of radiation, causing that region to collapse directly into a black hole. No star, no supernova, just density fluctuations in the primordial soup. Primordial black holes formed this way could have a wide range of masses. They could have formed with masses comparable to the Sun or greater, potentially explaining the seeds of supermassive black holes that became the giants we see today. But they could also have formed at much smaller scales. A primordial black hole with the mass of a large asteroid, one with the mass of a mountain, One, the mass of a rhinoceros, roughly 500 to 1,000 kilograms, squeezed into a volume smaller than a proton. These subatomic primordial black holes are sometimes called black hole rhinos, a shorthand that captures something genuinely strange about the idea. A black hole no larger than a proton, but with the mass of an adult rhinoceros. It would behave gravitationally like the object it mimics, but it would be invisible, undetectable by most instruments, and potentially all but impossible to find. For decades, the dominant argument against such tiny primordial black holes surviving to the present day was Stephen Hawking's theory of black hole radiation. In 1974, Hawking showed through a combination of quantum mechanics and general relativity that black holes are not completely black. They emit thermal radiation due to quantum effects near their event horizons. This radiation carries energy away from the black hole, causing it to lose mass very slowly over time. Smaller black holes emit more strongly relative to their size, which means they evaporate faster. Hawking's calculations suggested that primordial black holes below a certain mass threshold, roughly 10 to the power of 11 kilograms, would have had lifetimes shorter than the current age of the universe. By now, they would have evaporated entirely, ending in brief bursts of high-energy radiation. Any black hole rhino that formed in the first moments of the universe should have dissolved long ago. That was the conventional expectation. Then, in April of 2024, a paper published in the monthly notices of the Royal Astronomical Society introduced a complication. The study found that at very small scales, Hawking radiation does not necessarily continue at the same rate all the way to zero mass. Quantum gravity effects, which are poorly understood and represent one of the deepest unsolved problems in physics, may cause the evaporation process to slow dramatically as the black hole approaches extremely small sizes. The black hole might shrink and shrink until it reaches a stable minimum size, a Planck-scale remnant that stops evaporating entirely. If that is correct, every black hole rhino that formed in the first second of the universe could still be out there. Billions of them, trillions, invisible, drifting through the galaxy, each one carrying the mass of a large land animal in a volume smaller than an atomic nucleus. This connects to a much larger unresolved problem in cosmology, the nature of dark matter. Astronomers have known since the 1970s that the amount of gravitational influence observed in and around galaxies cannot be explained by the matter we can see. Stars, gas, dust, planets, they do not add up to enough mass to account for the rotation curves of galaxies or the behavior of galaxy clusters under mutual gravity. Something else is there, pulling without being seen. This unseen component is called dark matter. Dark matter makes up roughly 27% of the total energy content of the universe. Ordinary matter, everything made of protons and neutrons, accounts for only about 5%. The remaining 68% is dark energy, even more mysterious and not relevant here. But dark matter is real, inferred from its gravitational effects on everything around it, and we have no confirmed detection of any particle that could explain it. Black holes, particularly ones without accretion disks, are dark by nature. A primordial black hole that formed in the early universe from pure density fluctuations, with no surrounding star and no infalling gas cloud to generate an accretion disk, would be essentially invisible. It would not emit light. It would not emit radio waves. You could not detect it with a standard telescope. Scientists have considered and largely rejected the idea that large black holes account for dark matter. If there were many black holes of stellar mass drifting through and around the Milky Way, we would see their gravitational effects on starlight through a phenomenon called gravitational lensing. When a massive object passes between us and a distant star, its gravity bends the star's light, causing the star to appear briefly brighter. This effect, called microlensing, has been used to search for dark matter candidates in the galactic halo. Surveys like the Macho Project and Eros found that large compact objects cannot account for most of dark matter, but tiny primordial black holes, black hole rhinos, would produce gravitational lensing effects too small to detect with existing surveys. Their individual gravitational signatures would be too faint and too brief. The constraints from microlensing surveys do not rule them out. There is a window in the mass range of primordial black holes, roughly between 10 to the power of 17 grams and 10 to the power of 22 grams, where primordial black holes remain viable dark matter candidates. This range actually includes masses in the general vicinity of black hole rhinos and similar objects. The possibility, not yet confirmed but not ruled out, is that much of what we call dark matter in the outer regions of galaxies is a vast invisible population of these tiny primordial relics, a swarm of subatomic-sized but asteroid-massed black holes, each one a perfect gravitational phantom. Thinking about what that means for any civilization that might attempt to travel between galaxies is unsettling in a particular way. The space between galaxies, the intergalactic medium, is not empty. It contains diffuse gas, magnetic fields, and possibly these invisible black holes scattered throughout. A spacecraft crossing that void might encounter one with essentially no warning, not because the black hole would announce itself with a bright accretion disk or strong radio emissions. It would simply be there, a gravitational anomaly with no optical counterpart, traveling through the void on its own ancient trajectory. Whether such a crossing would necessarily be fatal depends on the encounter geometry, the mass of the black hole, and the proximity of the pass. A direct hit would be catastrophic, but even a near miss at very close range could distort the spacecraft significantly. The tidal forces near a sufficiently compact object are powerful even at low masses, because tidal forces depend not just on mass, but on proximity to the object. This is, for now, a thought experiment. We do not currently have the ability to travel between galaxies, but the physics underlying the concern is real, and it adds a dimension to the question of galactic travel that most discussions about interstellar missions do not include. The broader issue remains. We do not know whether primordial black holes exist. We do not know whether Hawking radiation really slows at Planck scales. We do not know whether any fraction of dark matter is composed of these objects. These are open questions with no agreed answers. What we have is a growing collection of circumstantial evidence that black holes are more varied and more numerous in their origins than the stellar collapse model implied. The James Webb Space Telescope is the primary driver of this shift. Its ability to resolve objects in the very early universe, just a few 100 million years after the Big Bang, has revealed a cosmic landscape that does not fit the older models without modification. The story of LID 568 adds another layer to this. LID 568 is a black hole located between 12.1 and 12.3 billion light-years away. It is so distant that its light has been stretched by the expansion of the universe entirely into the infrared range, making it invisible to ordinary optical telescopes. It required the combined power of the Chandra X-ray Observatory's Cosmos Legacy Survey and the James Webb Space Telescope to detect it at all. Even so, its entire host galaxy appears as little more than a compact red smudge at the edge of Webb's resolution. What made LID 568 significant was not its distance or its faintness. It was what the X-ray emissions from its accretion disk revealed about how fast it was eating. Analysis of those emissions showed that LID 568 is accreting matter at approximately 40 times the Eddington limit, not slightly above, 40 times above. It is consuming mass at a rate that standard models say should be physically impossible for sustained accretion. There are mechanisms by which black holes can temporarily exceed the Eddington limit. One involves the geometry of the jets that many accreting black holes produce. If the radiation from the accretion disk is collimated into narrow jets directed away from the infalling matter, the radiation pressure in the other directions is reduced, allowing material to continue falling in without being blown away. Another mechanism involves a brief phase of super-Eddington accretion in which the black hole grabs material faster than the radiation pressure can respond, a kind of momentum-based gluttony before the physics catches up. Neither mechanism allows indefinite super-Eddington accretion, but either might sustain elevated accretion rates for long enough periods to be relevant. LID 568 is the clearest observed example to date of a black hole exceeding the Eddington limit. Its existence does not resolve the problem of early supermassive black holes, but it demonstrates that the limit is not absolute. It can be broken, at least temporarily. Combined with the direct collapse hypothesis and the growing evidence from Webb's early universe observations, the picture that emerges is one of early black holes growing through a combination of mechanisms, born large through direct collapse, and capable of feeding faster than the standard model predicted. This matters because it has implications for how we understand galaxy formation as a whole. For decades, the dominant model assumed that stars came first and black holes grew from them. The sequence was: gas cloud collapses, stars ignite, massive stars die in supernovae, stellar black holes form. Stellar black holes grow over billions of years. Galaxies were the product of star formation, and supermassive black holes were a downstream consequence. The newer picture, suggested by Webb's observations, inverts some of this. Massive black holes may have seeded galaxy formation rather than following from it. Early supermassive black holes, formed through direct collapse in dense primordial gas clouds, may have gravitationally anchored the accumulation of matter around them, stimulating star formation and galaxy growth. If that is true, then black holes are not a byproduct of galactic evolution. They are a cause of it. That shift in perspective has significant consequences for cosmological models. It means the early universe was populated with massive gravitational anchors before it was populated with many stars. It means the star formation rates in the early universe were shaped in part by the presence of supermassive black holes. And it raises new questions about the feedback loops between black hole growth, accretion disk luminosity, and the surrounding galaxy, including how Eddington violating accretion episodes affected the galactic environments they occurred in. These questions are not fully answered. They are the active frontier of observational cosmology and theoretical astrophysics right now. On a parallel track, and using fundamentally different instruments, another branch of physics has been contributing new information about black holes through gravitational waves. In September of 2015, instruments at the Laser Interferometer Gravitational Wave Observatory, known as LIGO, detected a disturbance in spacetime so small it moved the observatory's 4-kilometer arm by 1/1000th the width of a proton. The event that caused that disturbance was the merger of two black holes, one with 29 solar masses and one with 36, located 1.66 billion light-years away. In the final 20 milliseconds of their inspiral and collision, they released energy equivalent to 50 times the combined light output of every star in the observable universe. That is not a misstatement. 50 times the light of all stars in the observable universe, released in 20 milliseconds, from two objects merging 1.66 billion light-years away. The residual disturbance, after traveling that distance for 1.66 billion years, was barely measurable by the most sensitive instruments humanity has ever built. Gravitational waves are one of the more abstract predictions of Einstein's general theory of relativity. The theory describes spacetime as a four-dimensional fabric that is curved by the presence of mass. When massive objects accelerate, they do not merely redistribute that curvature. They send ripples through it. These ripples propagate outward at the speed of light in all directions, gradually weakening as they spread. When they pass through a region of space, they alternately stretch and compress distances in perpendicular directions. The stretching and compressing is real, a physical distortion of space itself, not an optical illusion. Einstein predicted these waves in 1916. He also doubted they would ever be detectable, because the distortions they produce at any observable distance from their source are so vanishingly small that no instrument then conceivable could measure them. He was right about the difficulty. It took nearly a century of technological development before an instrument sensitive enough to detect them existed. LIGO is essentially a large-scale interferometer. It operates by splitting a laser beam and sending the two halves down two perpendicular 4-kilometer tunnels, called arms, each evacuated to 1/1,000,000th of atmospheric pressure to eliminate interference from air molecules. At the end of each arm is a mirror. The laser light bounces between the mirror and a recycling mirror at the entry point approximately 300 times before recombining at the beam splitter, effectively increasing the optical path length from 4 kilometers to 1,200 kilometers. When the beams recombine, they are compared for phase. In the absence of any disturbance, the two beams cancel each other out, and no light reaches the detector. Any difference in the length traveled by the two beams causes the beams to be out of phase when they recombine, producing a detectable signal at the photodetector. The sensitivity required to detect gravitational waves is extraordinary. LIGO's mirrors weigh 40 kilograms each and are suspended on silica threads to isolate them from ground vibrations. The optical cavities suppress quantum noise in the phase of the light by shifting it into the amplitude, which the instrument does not measure. The vacuum chambers achieve pressures comparable to those of deep space. Even with all these precautions, the observatory is surrounded by noise from seismic activity, atmospheric pressure changes, traffic, ocean waves, and thermal fluctuations in the mirrors themselves. Every detection requires careful separation of genuine signal from continuous background noise. LIGO operates as two observatories simultaneously, one in Hanford, Washington, and one in Livingston, Louisiana. A genuine gravitational wave signal must appear in both observatories with a time delay consistent with the speed of light travel between the two sites. This cross-correlation provides strong evidence against local noise sources producing false detections. Since the first detection in 2015, LIGO has recorded more than 80 black hole mergers across its first 3 operating runs. In August 2017, it detected the merger of 2 neutron stars, an event designated GW170817, which was simultaneously observed by 70 observatories around the world across the electromagnetic spectrum. That event marked the beginning of multi-messenger astronomy, the practice of studying the same cosmic event through both gravitational waves and light simultaneously, combining 2 completely different physical channels of information about the same source. The 4th observing run, begun in May of 2023 after 3 years of upgrades, brought improved mirror reflectivity, better vibration isolation, and reduced quantum noise. The Japanese underground detector KAGRA joined the network during this run. KAGRA is the first gravitational wave observatory built underground and the first to use cryogenic mirrors, cooled to cryogenic temperatures to reduce thermal noise. Early in its engineering run, LIGO scientists reported a candidate signal consistent with a neutron star being swallowed by a black hole, an event type that had never been confirmed before. Future upgrades planned for the late 2020s will increase mirror mass by a factor of 4 and shift to higher frequency lasers, improving sensitivity further. A proposed third-generation observatory called Cosmic Explorer would feature arms stretching 40 kilometers and 20 kilometers respectively, dramatically extending the range and frequency sensitivity. And a proposed space-based mission called the Laser Interferometer Space Antenna, or LISA, would deploy 3 spacecraft in a triangular configuration, 2.5 million kilometers on a side. That configuration would be sensitive to much lower frequency gravitational waves than LIGO can detect, opening up new source types including signals from the very early universe, from exotic objects like cosmic strings, and from supermassive black hole mergers across cosmological distances. LISA's planned launch date is 2037. Together, LIGO and its successors are contributing to our understanding of black holes in a way that complements and extends everything the James Webb Space Telescope is doing. Webb sees the universe through light, across a vast range of wavelengths. LIGO hears it through vibrations in spacetime itself. Neither is sufficient alone. Together, they are beginning to sketch a picture of black holes, their populations, their formation histories, and their extreme behaviors that is considerably richer and more complex than the picture we had 20 years ago. And alongside the gravitational wave discoveries and the deep field imaging from Webb, a quieter but equally interesting story has been unfolding in the study of microquasars. Quasars are among the most luminous objects in the universe. A single quasar can outshine the combined light of every other star in its host galaxy. They are powered by supermassive black holes consuming matter at high rates, producing accretion disks of superheated plasma, and in many cases, relativistic jets of charged particles that extend for thousands or millions of light years. When these jets interact with intergalactic magnetic fields, they emit radio waves. This radio emission is what gave quasars their original designation as quasi-stellar radio sources, eventually shortened to quasars. Quasars were first cataloged in the 1950s and 1960s as mysterious radio sources with no obvious optical counterparts. By the time astronomers confirmed what they were, nearly 3 decades of puzzling observations had accumulated. Today, quasars are understood well enough that we use them as standard candles and probes of the large-scale structure of the universe. What was not expected was that the Milky Way would contain its own scaled-down versions of these objects. Stellar mass black holes, the kind formed by supernova collapse, occasionally find themselves in close binary systems with ordinary stars. When a star's outer layers expand or the orbit brings the companion close enough, the black hole can begin pulling gas from the star's surface, forming a small accretion disk. In some cases, this accretion disk produces jets. These objects are called microquasars, and they are scattered throughout our galaxy. The first confirmed microquasar was discovered in 1979 and cataloged as SS433. It consists of a type, a supergiant star, orbiting a stellar mass black hole in a binary system. The black hole draws material from the supergiant, producing 2 jets of ionized plasma that extend outward from the black hole perpendicular to the accretion disk. What makes SS433 particularly interesting is its structure. There are 2 distinct jet systems. The inner jets extend just a couple of light years from the black hole before fatting. The outer jets appear approximately 75 light years out and span an additional 300 light years. We do not fully understand how these outer jets form, what they are made of, or why they terminate after 300 light years. A study conducted by the HESS collaboration, which operates an array of ground-based gamma-ray telescopes in Namibia, provided new clues. The outer jets of SS433 emit gamma-ray photons at surprisingly high energies, reaching over 10 trillion electron volts per photon. That is 10 trillion times more energy per photon than visible light carries. Ordinary thermal processes in stars or accretion disks cannot produce photons at those energies. The mechanism that explains this is called inverse Compton scattering. High-energy electrons in the jets collide with lower-energy photons passing through the system. In each collision, the electron transfers some of its energy to the photon, boosting the photon from the infrared or optical range up to gamma-ray energies. The HESS measurements showed that the highest energy gamma rays, those produced by the most energetic electrons, come from the innermost parts of the outer jets. Lower energy gamma rays come from progressively farther out along the jets. This spatial distribution is precisely what inverse Compton scattering predicts. Electrons lose energy as they travel down the jets and undergo repeated collisions with photons. So the photons they boost become less energetic the farther you go from the base. But this creates another puzzle. The electrons at the base of the outer jets appear to be traveling at greater than 99% of the speed of light. Their initial launch velocity from the black hole was calculated to be roughly 25% of the speed of light. Somewhere between launch and the outer jets, those electrons were accelerated by a factor of approximately 1 billion in energy. The proposed mechanism is called diffusive shock acceleration. At the base of the outer jets, complicated magnetic field configurations create a shock front. Each time an electron crosses this shock front, it receives a kick of additional energy. Because of the magnetic field geometry, electrons do not cross the shock front once. They diffuse back and forth, crossing it repeatedly, each crossing adding another boost. Over many crossings, individual electrons can be accelerated to energies in the hundreds of trillion electron volts, well above what a single crossing would produce. The gamma-ray spectrum observed by HESS is consistent with this mechanism. This result matters beyond SS433 itself. Microquasars are close enough that we can study the structure of their jets in spatial detail that is impossible for their distant supermassive counterparts. The physical processes driving jet formation, electron acceleration, and radiation in microquasars appear to be the same processes operating in the vastly larger quasars at the cores of distant galaxies. Studying the nearby version at high resolution allows us to test models of jet physics that apply across many orders of magnitude in scale. There is an irony here that is worth pausing on. The most powerful phenomena in the universe, supermassive black holes consuming matter at rates that outshine entire galaxies, are best understood through their small, quiet cousins sitting in the Milky Way's stellar population. The universe has distributed its secrets across scales in a way that invites comparison. Taking stock of everything, the picture of black holes that is emerging from the last several years of observation is one of remarkable diversity and surprising extremity. We have black holes forming through the direct collapse of gas clouds in the early universe, without stellar intermediaries. We have black holes exceeding the Eddington accretion limit by factors of 40. We have isolated supermassive black holes floating between galaxies with no obvious host. We have microquasars accelerating electrons to energies 1 billion times their launch values through repeated shock crossings. We have gravitational wave detectors recording the mergers of black holes and neutron stars at distances of billions of light years, measuring distortions in spacetime at scales smaller than a proton. And we have an unresolved theoretical question about whether tiny primordial black holes with masses comparable to large animals might constitute a component of the dark matter halos surrounding galaxies. None of these discoveries is fully understood. The mechanism by which LID 568 sustains 40 times the Eddington accretion rate is not established. Whether direct collapse black holes are the primary seeds of supermassive black holes or only a contributing pathway is not settled. Whether Hawking radiation genuinely slows to a halt at Planck scales, potentially leaving behind stable remnants, has not been confirmed by any observation. The composition of dark matter, including whether any fraction of it consists of primordial black holes, remains one of the most contested open questions in physics. What is clear is that each new observatory adds a new dimension to the data. The James Webb Space Telescope operates in infrared, seeing through dust and stretching its view back to within a few 100 million years of the Big Bang. LIGO operates in gravitational waves, detecting events invisible to any electromagnetic telescope. The HESS Gamma Ray Telescope array detects the highest energy photons produced by local sources. X-ray observatories like Chandra detect the hot plasma of accretion disks. Upcoming facilities, including Cosmic Explorer, LISA, and the next generation of space telescopes, will extend coverage to frequency ranges and distances not currently accessible. The more channels we open, the more we find that black holes are not the simple, static, singular objects implied by the term. They are dynamic, diverse, and still surprising. Every new observation has revealed something the models did not predict, or has confirmed something only tentatively expected. The universe continues to return results that are stranger than the frameworks built to explain them. What scientists are working to understand now spans several overlapping fronts. Theorists are refining models of super Eddington accretion, trying to determine which physical configurations allow sustained above-limit feeding, and for how long. Observers are scanning Webb's data for more isolated supermassive black holes like the one found in July 2025, hoping to build a statistical sample large enough to constrain how common direct collapse is. Gravitational wave astronomers are analyzing the catalog of mergers from LIGO's fourth run, looking for signatures of unusual mass combinations that might indicate intermediate mass black holes or exotic compact objects. Theoretical physicists are working on quantum gravity models that might resolve the fate of Hawking evaporation at Planck scales and determine whether primordial black hole remnants are a physically realistic possibility. The fate of primordial black holes in particular is tied to some of the deepest unresolved problems in fundamental physics. Hawking's original calculation connecting quantum field theory to black hole thermodynamics was a landmark result, but it was derived in a regime, small black holes near their final evaporation, where quantum gravity effects are expected to be important. Quantum gravity remains an unsolved theory. The standard treatments of Hawking radiation do not include quantum gravity corrections, because we do not have a complete theory of quantum gravity to include. The 2024 paper suggesting evaporation slows dramatically is one attempt to incorporate such corrections, but it is not the final word. Every one of these threads connects back to a central theme. The formation, growth, and physical behavior of black holes encodes information about the conditions of the early universe, the nature of quantum spacetime, and the large-scale structure of matter we cannot directly observe. Black holes are not merely exotic endpoints of stellar evolution. They appear to be fundamental participants in the history of the cosmos, present from its earliest moments, and influencing the development of structure across billions of years. The instinct, when hearing about another black hole discovery or another record broken, might be to expect that each new finding closes a question. The pattern instead has been that each one opens at least one more. Supermassive black holes existed too early. Black hole rhinos might not have evaporated. An isolated black hole floats between galaxies. A distant black hole eats at 40 times the allowed rate. Electrons in a Milky Way jet accelerate to 1 billion times their starting energy. And behind each of these specific surprises is the same underlying signal. The universe has been building and operating these objects for far longer, in far more ways, and under far more extreme conditions than the models expected. That is not a statement about the failure of science. It is a statement about its ambition. The models were constructed on the best available evidence. The new observations reveal where they need to expand. The expansion is happening now, driven by instruments of unprecedented capability aimed at the oldest and most energetic phenomena in the universe. What they will show in the years between the current run of LIGO observations and the launch of LISA, between the early universe images Webb is currently producing and whatever follows it, is genuinely unknown. If the recent record is any guide, whatever they find will be strange in ways we are not yet predicting. That is the current situation with black holes, not a solved problem being confirmed by new data, but an expanding frontier where each new instrument reveals that the frontier was larger than we thought. If any of this has made you want to follow along as that frontier expands, the best way to stay current is to keep watching, keep asking, and keep your expectations open. The universe has consistently exceeded them. To fully appreciate how far our understanding has evolved, it is worth stepping back and examining each of these discoveries in greater depth, tracing the chains of reasoning that connect them, and understanding what they collectively imply for our picture of the cosmos. Start with the Eddington limit, because it is the thread that connects so many of these stories. Arthur Eddington was one of the dominant figures in early 20th century astrophysics. Among his many contributions was the first observational confirmation of general relativity. During the solar eclipse of 1919, he measured the bending of starlight around the sun and found it matched Einstein's prediction. But Eddington also made foundational contributions to stellar physics, and the limit bearing his name emerged from his work on what keeps stars from collapsing under their own gravity. Stars are in continuous equilibrium between two opposing forces. Gravity pulls inward. Radiation pressure pushes outward. The energy generated by nuclear fusion in the stellar core streams outward as photons, and those photons carry momentum. When they interact with the surrounding plasma, they impart a tiny outward push. Summed over all the photons produced by a sufficiently luminous star, this radiation pressure is enough to support the star against gravitational collapse. Eddington recognized that there was a critical luminosity above which radiation pressure would overwhelm gravity. A star that radiated at this level, or above it, would begin blowing itself apart. The specific value of this luminosity depends on the mass of the object. A more massive object produces stronger gravity, and therefore can sustain higher luminosity before the outward radiation pressure wins. The ratio of luminosity to mass at the Eddington limit is essentially constant for objects dominated by hydrogen plasma. roughly 30,000 solar luminosities per solar mass. For black holes, the calculation is slightly different because the black hole itself does not radiate. The relevant luminosity is that of the accretion disk. As matter spirals inward, gravitational energy converts to heat through friction and viscosity in the disk. That heat radiates. When the accretion rate is high enough, the disk becomes luminous enough that the radiation pressure it produces exceeds the gravity pulling new material inward, shutting off further accretion. In practice, the Eddington limit for black holes sets a maximum accretion rate that depends on the black hole's mass. More massive black holes have stronger gravity, can sustain higher accretion luminosity before radiation pressure takes over, and therefore can in principle consume matter faster in absolute terms. But the ratio of accretion rate to mass, sometimes called the Eddington ratio, is still bounded. The problem this creates for the early universe is straightforward. The most massive black holes we can observe from when the universe was only a few 100 million years old have masses of hundreds of millions to a billion solar masses. To grow from a stellar mass seed to those masses in that time, even at the Eddington limit continuously, the seed black hole would need to have started with a mass of at least several hundred solar masses and fed without interruption. Getting that much mass concentrated into a black hole seed that early, without direct collapse, requires either improbably massive first-generation stars or improbably rapid mergers of stellar black holes. Neither is entirely impossible. Both require conditions quite different from what we observe in the present-day universe. The direct collapse scenario sidesteps much of this difficulty. If the seed was not a stellar remnant of a few hundred solar masses, but instead a direct collapse object of tens of thousands to hundreds of thousands of solar masses, the growth problem largely disappears. A seed that massive has a substantially longer runway to the Eddington limit and needs far less time to reach the masses we observe. What conditions would allow direct collapse to occur? The primary requirement is the suppression of star formation in the collapsing gas cloud. If the cloud fragments into stars before it collapses to a black hole, you get a star cluster, not a single massive object. For the cloud to collapse as a whole rather than fragmenting, you need to prevent the gas from cooling efficiently. Molecular hydrogen and carbon monoxide are the primary coolants in ordinary interstellar gas. If those molecules are dissociated by ultraviolet radiation from nearby star-forming regions, the gas cannot fragment and cool, and instead falls inward as a whole. The result can be an object of 10,000 to 100,000 solar masses that collapses directly into a black hole, or through an intermediate supermassive star that quickly collapses. Conditions favorable for this kind of direct collapse would have been more common in the early universe than today. The first generation of stars, called population 3 stars, were likely extremely massive by present standards, possibly hundreds of solar masses each, and their ultraviolet output was prodigious. They could have irradiated neighboring gas clouds intensely enough to suppress molecular cooling. At the same time, the density of the universe was higher and gas clouds were closer together, making large-scale collapse events more frequent. As the universe aged and evolved, population 3 stars gave way to subsequent generations. The interstellar medium became enriched with heavy elements, and the conditions favoring direct collapse became rarer and rarer. This would explain why direct collapse black holes appear to be a phenomenon of the early universe, and why we do not see them forming today. The observation in July 2025 of an isolated supermassive black hole between two colliding galaxies fits this picture reasonably well. The researchers who identified it noted that the black hole's location between the two galaxies, rather than at the center of either, is consistent with it having formed in an overdense region of the intergalactic medium during an early epoch of the universe, when direct collapse was more favorable. As the universe evolved around it, it did not grow a galaxy of its own. It sat there, accreting slowly or intermittently, while the two larger galaxies formed and developed beside it. This is speculative. Confirming or refuting it will require more observations, more examples of similar isolated supermassive black holes, and more detailed modeling of how such objects would evolve over cosmic time. The James Webb Space Telescope is the primary tool for finding more of them, and its ability to image galaxies and their environments across most of the observable universe at infrared wavelengths gives it unmatched reach for this kind of survey work. The story of QS01, the black hole in the chemically primitive galaxy, adds a different kind of constraint to the same puzzle. The chemical signature of a galaxy records its stellar history. Stars produce heavier elements through nuclear fusion over their lifetimes. When stars die, especially in supernovae, they eject those elements into the interstellar medium. Subsequent generations of stars form from gas enriched by these earlier generations, and the cycle continues. By the time a galaxy has undergone several generations of star formation, its gas and its new stars carry a characteristic chemical fingerprint, significantly elevated abundances of oxygen, carbon, nitrogen, magnesium, iron, and other elements heavier than helium. The galaxy hosting QS01 had almost no oxygen, 1% of the oxygen abundance in the Milky Way. That is a galaxy that has had very little stellar processing. It has not gone through many generations of stars. Its chemical inventory is still close to primordial, and yet it hosts a supermassive black hole. If stellar processes are minimal, the black hole could not have grown from stellar remnants in the usual way. It had to have originated through a non-stellar mechanism. The most plausible candidate, given the theoretical landscape, is direct collapse. The black hole formed from the gas of the early universe, before that gas had been significantly processed by stars. The galaxy then began forming stars afterward, perhaps partly triggered by the gravitational influence of the black hole itself, but those stellar generations are still early. The chemical record reflects that immaturity. This is a compelling piece of evidence, but it is indirect. It demonstrates consistency with the direct collapse hypothesis rather than proving it. The definitive test would be to observe a direct collapse event in progress, or to find the theoretical signature of a direct collapse black hole at an early enough stage of its evolution that its origin mechanism is still encoded in its properties. That is a harder observation to make. Direct collapse events in the early universe would be extremely luminous, potentially visible to Webb at the relevant distances, but distinguishing them from quasars or other bright early universe sources requires very specific spectral features. The theoretical signatures are still being worked out, and the observational capability to detect them is only now coming online with Webb and its successors. Meanwhile, the population of gravitational wave events from LIGO's fourth observing run is beginning to reveal the demographic landscape of merging black holes in a new way. Every black hole merger detected by LIGO provides several pieces of information: the masses of the two merging objects, their spins, the distance to the event, and the properties of the final merged object. Over many detections, these numbers build up into a distribution, a statistical portrait of the black hole population in the universe. Several things stand out from the accumulated data. The mass distribution of merging black holes shows a clustering around certain mass values, with a noticeable feature around 30 to 40 solar masses. There are also events at higher masses, including some that fall in a mass range where stellar evolution theory predicts black holes should not be able to form, the so-called parent stability mass gap between approximately 40 and 130 solar masses. Stars in this mass range are predicted to undergo parent stability supernovae, explosive events that leave no compact remnant. Black holes in this mass gap should not exist if they came from single stellar evolution. And yet some of the merger events detected by LIGO involve objects with masses that seem to fall in this range. They could be the products of previous mergers, black holes that formed from the coalescence of smaller black holes rather than from stellar collapse. If so, they are a new class of black hole, a second-generation merger product, and their existence tells us something about the environments in which black hole mergers occur. Environments dense enough for merger products to encounter new merger partners before being ejected. Dense star clusters, galactic nuclei, and certain types of active accretion environments are candidates. Alternatively, some of these mass gap objects might be intermediate mass black holes, a class of object predicted to exist between stellar black holes and supermassive black holes, but for which direct observational evidence has been frustratingly sparse. Intermediate mass black holes, with masses between 100 and 100,000 solar masses, are expected to exist as the products of runaway mergers in dense stellar environments, and as the scaled-down ancestors of supermassive black holes. Their absence from well-characterized catalogs has been one of the puzzles of observational astrophysics. If LIGO is beginning to detect them, or their merger products, that gap in the observational record may be starting to fill. The neutron star events are equally informative. The August 2017 neutron star merger, GW170817, produced an electromagnetic counterpart detected across the spectrum from gamma rays to radio waves. The analysis method that does not rely on the same assumptions as traditional electromagnetic methods. The value obtained was consistent with, but had large uncertainties relative to, the values obtained from other methods. As more neutron star mergers are detected, the gravitational wave Hubble constant measurement will improve, potentially helping to resolve or constrain the ongoing tension between different methods of measuring the universe's expansion rate. That tension, sometimes called the Hubble tension, is itself one of the pressing open problems in cosmology. Different methods of measuring how fast the universe is currently expanding give slightly but significantly different answers. The local distance ladder, based on measuring distances to nearby galaxies through various calibrated steps, gives a value around 73 kilometers per second per megaparsec. The value inferred from the cosmic microwave background, the afterglow of the Big Bang, gives a value around 67 kilometers per second per megaparsec. The difference is about 9%, which is small in absolute terms but large relative to the measurement uncertainties. If the discrepancy is real and not due to systematic errors, it implies that our current cosmological model is missing something. Gravitational waves provide an independent measurement that bypasses both methods and will eventually distinguish between the possibilities. The connection between gravitational waves and black hole physics is direct. Every merger LIGO detects is a test of general relativity in the strong field, highly dynamic regime that no other observation can access. The predictions of general relativity for how two black holes inspiral and merge, how they ring down after the merger, and how gravitational waves from such events propagate through spacetime have all been tested against LIGO data. So far, general relativity passes every test, but the tests have finite precision, and future detectors with better sensitivity will constrain deviations from general relativity more tightly. If there are corrections to general relativity at strong fields or small scales, those corrections would affect the predictions for gravitational waveforms. Sufficiently sensitive future detectors might see discrepancies between observed waveforms and the predictions of pure general relativity. Any such discrepancy would be a landmark result, potentially pointing toward the quantum gravity theory that has so far eluded physicists. This brings us back to the primordial black hole question in an interesting way. One signature predicted for Hawking radiation, if it exists, and if primordial black holes are reaching their final evaporation phase now, is a burst of high-energy gamma rays. The energy scale of this burst would be characteristic of the black hole mass. Gamma ray observatories have searched for such bursts without finding convincing candidates. The absence of detections constrains the abundance of evaporating primordial black holes in certain mass ranges. But the constraints depend on the assumed properties of Hawking radiation, and if quantum gravity corrections cause evaporation to slow or stop at Planck's scale, the expected signature would not occur. The absence of detections cannot rule out stable Planck mass remnants. The question of Planck scale physics is one of the frontiers where theoretical physics and observational astronomy are approaching each other from opposite directions. Theorists are building models of quantum gravity that make predictions about the behavior of black holes at extremes of mass and temperature. Observers are searching for signatures of those extremes through gamma ray bursts, gravitational wave ringdom, and the statistical properties of merging black hole populations. Neither side has yet produced a definitive signal, but the tools are improving. Consider what a space-based gravitational wave detector like LISA would be capable of. Operating in space eliminates the seismic noise that limits ground-based detectors. A triangle of spacecraft separated by 2.5 million kilometers would be sensitive to gravitational waves with frequencies between 1/10,000th and 1/10 of a hertz, far lower than LIGO's sensitive band. Lower frequency gravitational waves are produced by more massive and more slowly evolving systems. Supermassive black hole mergers at cosmological distances, the gradual inspiral of compact objects into supermassive black holes over years or decades, and possible primordial gravitational wave backgrounds from the very early universe. The inspiral of a compact object, possibly a stellar mass black hole or neutron star, into a supermassive black hole is a particularly information-rich source for LISA. These events, called extreme mass ratio inspirals, produce gravitational wave signals that last for thousands of orbits before the final plunge. Each orbit maps the spacetime around the supermassive black hole with exquisite precision. Analysis of these signals would provide the most detailed tests of general relativity ever conducted, and would reveal the structure of spacetime near a supermassive black hole to an accuracy no electromagnetic observation could approach. If there are subtle deviations from general relativity near supermassive black holes, LISA would find them. If the spacetime outside supermassive black holes is exactly as general relativity predicts, LISA would confirm that to unprecedented precision. Either result advances the field substantially. Meanwhile, the electromagnetic picture of black holes continues to develop in parallel. The Event Horizon Telescope, which produced the first direct image of a black hole shadow in 2019 for M87 and in 2022 for Sagittarius A*, is planning improvements that will allow it to capture movies of black hole accretion dynamics rather than still images. The next generation Event Horizon Telescope, using more stations, wider bandwidth, and possibly space-based components, would have the resolution to image the immediate environment of the black hole event horizon at previously impossible scales. Combined with gravitational wave data from LIGO and eventually LISA, and with the high redshift imaging from Webb and its successors, the observations available to black hole astronomers within the next 2 to 3 decades will be qualitatively different from anything available today. They will span the full mass range of black holes, from stellar to supermassive. They will span the full cosmic history, from the first black holes formed in the primordial universe to the quiet ones sitting at the centers of present-day galaxies. And they will access the physics of black holes through multiple completely independent channels: electromagnetic radiation at all wavelengths, gravitational waves across multiple frequency bands, and potentially new types of signals not yet anticipated. In that context, the specific discoveries discussed here, the isolated supermassive black hole floating between galaxies, QS01's chemically primitive host galaxy, LID 568 exceeding the Eddington limit by a factor of 40, the 2024 theoretical result suggesting primordial black hole evaporation might slow to a halt, the HESS measurements of shock-accelerated electrons in SS433's jets, and the expanding catalog of mergers from LIGO's fourth run are best understood not as isolated puzzles, but as data points in a rapidly growing dataset. The emerging picture is one in which black holes are not merely the dramatic endpoints of stellar evolution, not just the silent gravitational anchors at the centers of galaxies, but active participants in the physical evolution of the universe from its earliest moments. They shaped the environments in which the first stars formed. They anchored the growth of the first galaxies. They regulated star formation rates through feedback from their accretion. They merged repeatedly, growing through successive generations of mergers and accretion events. They scattered high-energy particles through their jets, contributing to the cosmic ray population that permeates the galaxy. And they may constitute a component of the dark matter that glues galactic structure together if the smallest ones avoided evaporation through quantum gravity effects. Each of these roles, if confirmed, adds another dimension to a story that began with the simple observation that very massive stars could collapse to points of infinite density. From that starting point, the physics has expanded in every direction, to smaller black holes that might survive indefinitely, to larger black holes that might have formed without any stellar step, to black holes that eat faster than they should be able to black holes detected not by any kind of light, but by the trembling of spacetime itself. The central lesson of the past decade of black hole astronomy is that these objects are stranger than any simple model accounts for, and that the universe has had nearly 14 billion years to produce, evolve, and diversify them in ways that the models we build in a few human lifetimes have not fully captured. That gap between model and reality is not a failure. It is the engine of progress. Every discrepancy between what we expected and what we found has pointed the way toward a deeper understanding. The super Eddington accretion of LID 568 suggests mechanisms of matter inflow that were underappreciated. The isolated supermassive black hole suggests formation pathways that bypass the stellar step. The slowing of Hawking evaporation at Planck scales, if confirmed observationally, would require a framework for black hole thermodynamics that incorporates quantum gravity in a way the current theory does not. None of this will be resolved quickly. The timescales involved in astrophysics research, from proposal to funding to construction to first light to data analysis to publication, are measured in years and decades. LISA will not launch until 2037. The next generation of ground-based gravitational wave detectors will come online in the 2030s. Webb has years of observing time ahead of it. The picture will clarify slowly, as high-quality data accumulates and theoretical models are revised and extended to accommodate it. What makes this particular moment in astrophysics unusual is the simultaneity of progress across multiple fronts. In previous decades, advances in our understanding of black holes tended to come from one direction at a time. Radio astronomy revealed quasars. X-ray astronomy revealed the hot plasma of accretion disks. Optical spectroscopy revealed the chemical signatures of high redshift objects. Each new wavelength window opened a new perspective, but they were opened sequentially. What is happening now is something different. Webb is imaging the early universe at infrared wavelengths. LIGO is recording gravitational wave mergers in the audio frequency band. Gamma-ray telescopes are probing the highest energy processes near black holes in the galaxy. X-ray observatories are analyzing the spectra of distant accretion disks. Ground-based optical telescopes are characterizing the host galaxies of black holes detected in other wavelengths. All of these observations are happening simultaneously, and they are increasingly being connected to the same events and the same populations of objects. The merger detected in gravitational waves can, in some cases, be localized well enough to be observed in electromagnetic light. The gamma-ray signature of a microquasar can be compared with its radio jet morphology and its X-ray accretion spectrum. The high redshift black holes found by Webb can be cross-referenced with X-ray catalogs from Chandra and with radio catalogs from ground-based arrays. Multi-messenger astronomy, the practice of combining information from multiple physical channels about the same objects and events, is transforming from an occasional achievement to a standard methodology. This convergence means that the constraints on any given theory become much tighter when multiple independent observations must all be simultaneously explained. A model that accounts for the luminosity of an early universe black hole, but not its mass growth rate, is not a good model. A model that explains super Eddington accretion theoretically, but predicts observational signatures inconsistent with what Webb and Chandra see, is not a good model. The multi-messenger approach enforces a consistency requirement that each individual measurement alone cannot impose. For primordial black holes specifically, the multi-messenger approach is particularly relevant. The constraints on their abundance come from multiple independent sources: microlensing surveys, cosmic microwave background measurements, gamma-ray burst searches, and gravitational wave background measurements. Each constrains a different mass range and a different population of primordial black holes. Together, they carve out the surviving windows in parameter space, where primordial black holes could constitute a significant fraction of dark matter. The results, as of the mid-2020s, are complex. Large primordial black holes, those with masses comparable to stars or larger, are ruled out as the dominant component of dark matter by the microlensing and gravitational wave constraints. Very small primordial black holes, those with masses below roughly 10 to the power of 11 kilograms, are constrained by the expected Hawking radiation they should have emitted, which would affect the cosmic microwave background and produce detectable gamma-ray backgrounds. But in an intermediate mass window, and potentially extending to Planck mass remnants if evaporation genuinely stops, primordial black holes remain viable. The 2024 theoretical result, suggesting Hawking evaporation slows near Planck scale, does not eliminate the observational constraints on intermediate mass primordial black holes. Those constraints come from the absence of microlensing events and from direct gravitational effects on surrounding matter, and they apply regardless of what happens at Planck scale. But it does open the door to a population of very tiny, extremely low-mass primordial black hole remnants that would be invisible to essentially every current observational technique. Their detection, if they exist, would require either a completely new type of instrument or a serendipitous encounter that reveals their gravitational signature in an unexpected context. In the very long term, the question of whether black holes leave Planck mass remnants connects to fundamental issues about information loss in black holes. Stephen Hawking's original formulation of black hole radiation implied that information about the matter that fell into a black hole is lost when the black hole evaporates. This conflicts with a basic principle of quantum mechanics, which holds that information is conserved. The conflict, known as the black hole information paradox, has been one of the central theoretical puzzles in physics for 50 years. One proposed resolution is that black holes do not completely evaporate. They leave stable remnants that carry the missing information. If those remnants exist, the information is not lost. The resolution is elegant but creates other problems. The remnants would be essentially undetectable, and their existence would need to be consistent with the rest of quantum mechanics and general relativity. Whether such a resolution is physically self-consistent is still actively debated. Another proposed resolution involves the concept of black hole complementarity and the holographic principle, which suggests that information falling into a black hole is somehow encoded in the radiation that escapes, just in a scrambled form that is practically impossible to decode. The mathematics behind this idea, developed largely through work on string theory and the AD-SCFT correspondence, is sophisticated and not yet fully understood. It does not predict immediate observable consequences for astronomical black holes. A third resolution, proposed more recently, involves contributions to the path integral of quantum gravity from what are called island configurations. The details are technical, but the upshot is that a correct accounting of all quantum gravity contributions to Hawking radiation predicts that information does escape from black holes, just very slowly and in a highly scrambled form. This approach avoids the information paradox without requiring stable remnants. All three resolutions remain contested. None has been definitively established. The question of information in black holes sits at the boundary between quantum mechanics and general relativity, exactly where the unknown theory of quantum gravity would need to apply. Until quantum gravity is understood, the information paradox will remain open. What connects all of these threads, from the observational discoveries by Webb and LIGO to the theoretical puzzles about quantum gravity and primordial black hole remnants, is the black hole as an object. It is the place in the universe where gravity is most extreme, where the curvature of spacetime is greatest, where quantum effects are expected to become important at the smallest scales, and where the physics we understand breaks down at the singularity. It is simultaneously the most classical object in general relativity, the endpoint of pure gravitational collapse, and the most quantum object in astrophysics, the place where quantum effects produce thermal radiation and potentially encode information in ways our best theories struggle to describe. That combination of properties makes black holes not just scientifically interesting, but philosophically significant. They are the places where the two great theories of 20th century physics, general relativity and quantum mechanics, are forced to confront each other, and where neither is entirely adequate. The 21st century challenge for fundamental physics is to develop a framework that handles both consistently, and black holes are the primary testing ground for whatever that framework turns out to be. Every observation that reveals a new aspect of black hole behavior, every merger detected by LIGO, every distant black hole imaged by Webb, every microquasar studied in gamma rays, adds to the dataset that any successful theory must explain. The dataset is growing rapidly, the theories are evolving to meet it, and the frontier keeps moving outward as each new instrument resolves what was previously invisible. That is the situation as of the middle of the 2020s. More data is coming, from instruments already operating and from instruments not yet launched. The questions raised by the recent discoveries will generate further observations designed to address them, and those observations will almost certainly raise new questions in turn. The history of black hole astronomy suggests that each time we look more carefully, we find something we were not expecting. What we can say with confidence is that black holes are not solved. They are not well understood background objects in an otherwise complete picture of the universe. They are active, dynamic, extreme, and in several respects still mysterious. The models are good enough to make useful predictions, but not complete enough to anticipate everything the universe has placed in our field of view. Closing that gap, or at least pushing it to smaller scales and higher energies, is the project that the next generation of instruments is designed to pursue. If the pattern holds, what they find will be worth following closely. There is one more dimension to this story that deserves careful attention, and that is the role of scale in our understanding of black hole physics. The universe operates black holes across an enormous range of masses. At the low end, if primordial black holes exist at the scales theorized, we are talking about masses measured in hundreds of kilograms, squeezed into volumes smaller than an atomic nucleus. At the high end, the most massive known black holes, found in the brightest and most distant quasars, contain tens of billions of times the mass of our Sun. The ratio between the most massive black hole we know and a black hole rhino spans roughly 45 orders of magnitude in mass, a range so large it defies intuitive comprehension. What is remarkable is that across this entire range, a single set of physical laws, Einstein's general relativity and the quantum mechanics of fields in curved spacetime, is expected to govern the behavior. The same equations that describe the gentle rippling of spacetime caused by two neutron stars orbiting each other also describe the extreme distortions near the singularity of a stellar mass black hole. The same principles that govern the Eddington limit for a stellar mass black hole in a binary system apply to the accretion disk of a supermassive black hole powering a distant quasar. This scale invariance, the tendency of black hole physics to reproduce the same basic behaviors across vastly different mass scales, is both one of the powerful predictions of general relativity and one of the things that makes black holes so useful as probes of fundamental physics. When you observe the same phenomenon at two very different scales and find that both conform to the same theoretical prediction, that consistency is strong evidence that the theory is capturing something real. The microquasar phenomenon is a perfect example. The jets produced by stellar mass black holes in binary systems share the same fundamental physics as the jets produced by supermassive black holes in quasars and radio galaxies. The mechanism of jet formation, the magnetic field configuration, the role of the black hole's spin in driving the jet, the relationship between accretion rate and jet power, all of these scale from stellar mass to supermassive in ways that are broadly consistent with scale-invariant physics. Studying SS433 at the level of detail that its proximity allows is, in a meaningful sense, studying the jets of quasars in distant galaxies. This is why the HESS results on SS433 have implications well beyond one nearby system. The diffusive shock acceleration of electrons to relativistic energies in the outer jets of a microquasar is a process that should operate, scaled up, in the large-scale jets of active galactic nuclei. The gamma-ray spectrum measured by HESS provides constraints on the energy distribution of electrons and the magnetic field strength in the jet environment. Those constraints, when translated to the relevant scales, apply to the jets of real quasars and radio galaxies, and can be compared against multi-wavelength observations of those larger systems. Similarly, the Eddington limit violation observed in LID 568 at cosmological distances has counterparts in local systems. Super-Eddington accretion, though not observed at 40 times the Eddington rate in nearby systems, has been confirmed at rates several times the Eddington limit in ultraluminous X-ray sources, which are thought to be stellar mass black holes accreting at extreme rates within nearby galaxies. The physics of super-Eddington accretion is accessible through these nearby systems, even though the cosmological context that makes LID 568 interesting. The question of how supermassive black holes formed so quickly in the early universe is specific to the high redshift regime. The combination of local laboratory systems like SS433 and high redshift observational targets like LID 568 and QSO-1 represents the dual approach that modern black hole astronomy takes to its most difficult questions. Study the physics in detail at low redshift, where the observations are more complete. Test the implications at high redshift, where the cosmological context is most constraining. It is also worth emphasizing what we do not yet have a good theory for. Beyond the specific open questions already mentioned, we do not have a complete understanding of jet formation. We know that jets are associated with spinning black holes and with organized magnetic fields in the accretion disk. The Blandford-Zienagic mechanism, proposed in 1977, describes how a spinning black hole can extract energy from its rotation through magnetic field lines threading the event horizon. That energy goes into powering a jet. The mechanism is elegant and consistent with many observations, but the detailed physics of how the jet is launched, collimated, and sustained over distances of thousands of light years is not fully understood. Numerical simulations of black hole accretion and jet formation have made enormous progress in recent years, but they still involve approximations and are computationally limited to relatively short time scales. We do not have a complete understanding of the feedback between black hole activity and galaxy evolution. Observations show that galaxies with larger bulges tend to have more massive central black holes, and that the properties of black holes and galaxies are correlated in ways that suggest they co-evolved. But the mechanism by which a black hole's accretion output, through radiation, jets, and outflows, regulates star formation in the surrounding galaxy is not fully characterized. The outflows from actively accreting black holes can heat or expel the gas in the host galaxy, shutting off star formation. This process is called AGN feedback, where AGN stands for active galactic nucleus, and it appears to be important in explaining why the most massive galaxies in the universe stopped forming stars at some point in cosmic history. But the details of how the energy is transferred from the black hole to the galaxy-scale gas, how much of the outflow actually escapes the galaxy, and how this depends on the black hole's mass and accretion rate are all areas of active research. We do not fully understand the relationship between the black hole spin and its observable properties. A black hole's spin, parameterized by a quantity between 0 and 1, representing the fraction of maximum possible angular momentum, affects the efficiency of energy extraction from the accretion disk, the nature of the innermost stable circular orbit, and the power of the jet. Measuring black hole spin observationally requires fitting the X-ray spectrum from the inner accretion disk, a technique that relies on assumptions about the geometry and emission properties of the disk that introduce systematic uncertainties. Better measurements of spin distributions across large populations of black holes would constrain models of how black holes grow and merge, but the current observational constraints are limited. We do not understand the connection between primordial black holes and the matter-antimatter asymmetry of the universe. The standard model of particle physics treats matter and antimatter symmetrically, yet the universe contains vastly more matter than antimatter. The mechanism responsible for this imbalance, called baryogenesis, is not established. Some models of baryogenesis involve the evaporation of primordial black holes, producing an asymmetric output of particles and antiparticles under certain conditions. If primordial black holes evaporated in the early universe, they could have contributed to or even caused the matter-antimatter asymmetry. Testing this idea requires understanding both the primordial black hole mass spectrum and the physics of Hawking evaporation at temperatures high enough to produce heavy particles, conditions that are far beyond laboratory access. These open questions span experimental, observational, and theoretical physics. They are not obscure or peripheral. They are central to our understanding of how the universe works and how it came to be in its present state. The next major observational milestones likely to shed light on these questions include the completion of LIGO's fourth observing run and the subsequent analysis of the accumulated event catalog. The fourth run is expected to produce a larger and more statistically powerful sample than the first 3 runs combined. Given the improved sensitivity, particular attention will be paid to events in the parent stability mass gap, which could indicate intermediate mass black holes or hierarchical merger products, and to any events that show departures from the waveform predictions of general relativity. The James Webb Space Telescope will continue its survey of high-redshift galaxies and their central black holes. Specific programs aimed at finding more isolated supermassive black holes, more chemically primitive host galaxies, and more extreme accretion events like LID 568 are already planned or underway. The statistical analysis of these samples will constrain models of early black hole formation and growth more tightly than any individual discovery can. Ground-based gamma-ray telescopes, including the upcoming Cherenkov Telescope Array, an international observatory involving more than 100 individual telescopes on 2 sites, will dramatically improve on the sensitivity and angular resolution of current gamma-ray observatories. The Cherenkov Telescope Array will be able to characterize the gamma-ray emission from microquasars like SS433 with much greater precision, resolving the spatial distribution of emission along the jets at shorter angular scales, and extending the energy coverage to higher values than HESS can achieve. The Square Kilometer Array, a radio telescope distributed across thousands of individual antenna stations in South Africa and Australia, will when complete provide unprecedented radio sensitivity and angular resolution across a wide frequency range. For black hole astronomy, its relevance includes imaging the radio jets of microquasars and active galactic nuclei at fine angular scales, detecting pulsars near Sagittarius A star that can be used as clocks to probe the black hole's spacetime, and contributing to the detection and characterization of nanohertz frequency gravitational waves through pulsar timing arrays. Pulsar timing arrays, networks of millisecond pulsars whose arrival times are monitored with nanosecond precision, are sensitive to gravitational waves with frequencies in the nanohertz range, far below the audio frequency range of LIGO. In 2023, multiple pulsar timing array collaborations simultaneously announced evidence for a gravitational wave background in the nanohertz band, consistent with the expected signal from the population of supermassive black hole binaries throughout the universe. This detection, still being confirmed and characterized as further data accumulates, would represent the first detection of gravitational waves in a completely different frequency band from LIGO, and would provide the first direct evidence that supermassive black holes do indeed merge on cosmological timescales, closing a loop in the theory of galaxy evolution. All of these instruments together represent a global scientific infrastructure dedicated in significant part to understanding black holes across their full range of masses, formation mechanisms, evolutionary states, and physical behaviors. The investment is justified not just by the intrinsic fascination of these objects, but by the scientific return they generate in understanding gravity, quantum mechanics, cosmology, and the physical history of the universe. Black holes are, in the end, both the most extreme gravitational objects and the most quantum mechanical objects in astrophysics. They are where the largest scale structure of spacetime meets the smallest scale structure of quantum fields. They are where the classical physics of collapsing matter meets the quantum physics of radiation and information. They are where the cosmic history of galaxy formation and dark matter meets the fundamental physics of particle interactions in the early universe. That convergence is what makes them scientifically central in a way that extends well beyond their spectacular visual appearance or their role in popular culture. Understanding black holes is not a peripheral project in fundamental physics. It is fundamental physics, applied to the most extreme laboratory the universe has provided. The discoveries of the past few years have made that laboratory stranger and richer than it was. The questions they have raised will drive research for the decades to come, and the answers, when they emerge, will almost certainly change not just our understanding of black holes, but our understanding of the physical universe that produced them. Perhaps the most striking feature of the current moment in black hole research is not any single discovery, but the sheer density of simultaneous breakthroughs across unrelated methodologies. A decade ago, our knowledge of black holes came almost entirely from two channels: electromagnetic observations across the spectrum from radio to gamma rays, and theoretical modeling. Both channels were productive, but they were limited in ways that were sometimes difficult to appreciate from inside the field. Electromagnetic observations can only see what emits light, or what blocks or distorts light from something behind it. A black hole that is not actively accreting, surrounded by no gas or dust, produces no electromagnetic signal of any kind. It is, by definition, dark. A stellar mass black hole drifting through interstellar space with no companion star is electromagnetically invisible. The same is true of a primordial black hole drifting through the galactic halo, or an intermediate mass black hole sitting in a sparse stellar environment without a nearby gas supply. Our electromagnetic observations of black holes are therefore a biased sample, heavily weighted toward black holes that happen to be actively consuming matter. Gravitational wave astronomy is fundamentally different in this respect. Gravitational waves are produced by the acceleration of mass, not by the emission of light. A binary system of two black holes in their final inspiral phase is a powerful gravitational wave source regardless of whether either black hole has an accretion disk. The mergers LIGO detects are not selected for biluminosity. They are detected when the energy released in the gravitational wave channel is large enough, and the merger close enough for the wave to reach detectable amplitude at Earth. This selection effect is different from, and to some degree complementary to, the selection effects of electromagnetic astronomy. The combination of the two is therefore particularly powerful. Electromagnetic observations reveal the properties of accreting black holes across cosmic history. Gravitational wave observations reveal the mass distribution, spin distribution, and merger rates of compact binary populations. Together, they constrain a far wider portion of the black hole parameter space than either can access alone. This complementarity is being extended further by advances in microlensing surveys. Wide-field optical surveys that monitor millions of stars simultaneously for the brief brightening caused by a foreground object passing in front of a background star are becoming increasingly capable of detecting the lensing signatures of very faint foreground objects. Current surveys like the Optical Gravitational Lensing Experiment and the Korea Microlensing Telescope Network are sensitive to lens masses from planetary to stellar scales. Future wide-field surveys like the Rubin Observatory's Legacy Survey of Space and Time will monitor billions of stars with rapid cadence, dramatically increasing the sample of microlensing events and potentially revealing populations of invisible compact objects, including stellar mass black holes, and, at the limits of sensitivity, the upper end of the primordial black hole mass range. Astrometric observations offer another complementary window. The Gaia Space Telescope, operating since 2014, measures the precise positions and motions of over 1 billion stars in the Milky Way. A black hole in a binary system with a luminous star will cause the star to wobble slightly as it orbits the center of mass. If the black hole is dark, no electromagnetic signal betrays the presence of the companion, but the wobble of the visible star reveals it. Gaia has already identified several candidate stellar mass black holes in this way, and future data releases will expand the sample substantially. Combined with LIGO merger statistics, the population of single and binary stellar mass black holes revealed by Gaia and future astrometric missions will provide a complete census of the stellar mass black hole population in the local galaxy. At the supermassive end, the approach is different. Very long baseline interferometry, the technique of combining radio telescopes across intercontinental baselines to achieve angular resolution equivalent to a telescope the size of Earth, has already imaged the shadows of the supermassive black holes in M87 and in Sagittarius A* at the center of the Milky Way. These images show the bright ring of emission from the accretion disk surrounding the dark central shadow where photons are captured by the black hole. The size and shape of this shadow are predicted precisely by general relativity given the black hole's mass and spin. Both images were consistent with those predictions, confirming general relativity in the strong field regime near the event horizon. The resolution of these images, while extraordinary, is still limited by the wavelength of the radio waves used and the effective baseline of the telescope array. Future extensions of the Event Horizon Telescope to space-based components would increase the effective baseline beyond Earth's diameter, improving the resolution and allowing not just static imaging, but time-resolved monitoring of accretion disk variability. The accretion disk around Sagittarius A* varies on timescales of minutes to hours, and future space-extended observations would be able to resolve the orbital motion of hot spots in the disk, directly measuring the rotational velocity of plasma near the innermost stable circular orbit, and constraining the black hole's spin with much higher precision. Precision measurements of black hole spin are important because spin is a conserved quantity that accumulates over the black hole's history. A black hole that grew predominantly through coherent accretion, fed consistently from one direction, will have a high spin aligned with the accretion disk. A black hole that grew predominantly through chaotic minor mergers and accretion from random directions will have a lower spin. The spin of Sagittarius A*, once measured precisely, will encode the merger and accretion history of the Milky Way's central black hole across cosmic time. In this sense, the spin of a single black hole is a fossil record of galactic history. Similar arguments apply to the supermassive black holes in other galaxies. As gravitational wave observatories extend their sensitivity to lower frequencies and larger binary separations, they will eventually detect the slow inspiral of supermassive black hole binaries formed in galaxy mergers. The gravitational wave signal from such a binary, measured over years to decades, will reveal the masses and spins of both black holes. Combined with electromagnetic observations of the host galaxy's current state, this will provide a complete picture of the merger event, how massive the two galaxies were, how the black holes were aligned before the merger, and what the product looks like afterward. This is galaxy archaeology performed through gravitational wave astronomy. It is not yet possible, but it is the direction that the field is moving, with LISA as the instrument that will first make it routine. The relationship between black hole spin and the direction of the jet is another area where the accumulating data will eventually constrain models in meaningful ways. Jets in active galactic nuclei are observed to precess, change direction over time, sometimes dramatically. This precession is thought to reflect the misalignment between the black hole's spin axis and the angular momentum axis of the surrounding accretion disk. When these are misaligned, general relativity predicts a precession of the disk and jet axis called lens-Thirring precession. The rate of precession depends on the black hole's spin and mass. Measuring the precession rate of jets in nearby active galactic nuclei, combined with independent mass measurements, provides another test of general relativity and another constraint on spin. For microquasars, the jet precession can be measured directly on human timescales. SS-433's jets precess with a period of about 162 days, a precession large enough that it was discovered in the first years of observation and has been studied in detail ever since. This system has served as a laboratory for lens-throwing precession physics for decades, and the HESS results on its gamma-ray emission fit into this broader context of detailed systematic study. Across all of these observational frontiers, theoretical astrophysics and numerical simulation are working in parallel to develop models capable of making quantitative predictions that can be tested against the increasingly precise data. Numerical relativity, the direct simulation of Einstein's equations on supercomputers, has made enormous progress in the past 2 decades. The first successful numerical relativity simulation of a black hole merger was achieved in 2005, and the field has advanced rapidly since then. Modern numerical relativity codes can simulate black hole mergers with arbitrary mass ratios and spin configurations, producing gravitational waveforms accurate enough to be used as templates for LIGO data analysis. They can also simulate the accretion disk dynamics, jet formation, and electromagnetic counterparts of merging neutron stars and neutron star black hole mergers. As the simulations become more realistic, including more complete treatments of magnetic fields, radiation transfer, and nuclear reactions, they are approaching the level where direct quantitative comparison with observations is meaningful. A simulation of a super Eddington accretion disk that predicts specific luminosity ratios, variability timescales, and outflow velocities can be tested against the detailed observations of LID 568 and similar systems. If the predictions match, confidence in the model grows. If they do not, the discrepancy points toward whatever physics the model is missing. This interplay between observation and simulation is the engine of progress in astrophysics. It is slower and less dramatic than the announcement of a single stunning discovery, but it is where the understanding deepens. The past decade has provided an unusually dense sequence of stunning discoveries. The coming decade will be characterized increasingly by the detailed follow-up work of testing models against the data those discoveries generated, and by the design and execution of observations specifically targeted at the open questions those discoveries raised. The open questions, stated plainly, are these. How did supermassive black holes reach their observed masses so quickly in the early universe? Is direct collapse a significant formation channel? And if so, what fraction of the present-day supermassive black hole population originated through this pathway? Does Hawking radiation genuinely slow at Planck scales? And if so, do stable Planck mass remnants exist? If they do they constitute any fraction of dark matter? Can super Eddington accretion be sustained for long enough periods to significantly affect supermassive black hole growth history? And if so, what physical mechanisms enable it? What determines the mass function of primordial black holes? And were the density fluctuations of the early universe consistent with significant primordial black hole production? What is the connection between black hole spin and the long-term history of accretion and mergers? None of these questions is trivially answerable. All of them have observational programs associated with them that are currently underway or planned. The answers, when they come, will arrive incrementally, each new piece of data moving the probability distributions over possible answers and gradually concentrating them around the correct ones. That is how science works in practice, not as a sequence of clean revelations, but as a gradual convergence of evidence from multiple directions onto an increasingly detailed and accurate picture. The picture of black holes that emerges from this process over the next few decades will be far more complete than what we have today, and in all likelihood far stranger than what we currently expect. That strangeness, whatever form it takes, is the most honest forecast available. The universe has consistently exceeded the strangeness of our best models. The black hole is the place where that pattern is most reliably observed. Whatever the next generation of instruments finds, the safe prediction is that it will surprise us, that the surprises will be grounded in real physics, and that working out the implications will be worth following carefully. If you found this exploration worthwhile, if the strangeness of primordial black holes and Eddington limit violations and gravitational wave detections at scales smaller than a proton resonated with something real about how extraordinary the physical universe is, then stay curious. This field is moving fast. The instruments are improving, the questions are getting sharper, and the universe, as reliably as ever, is not done being strange. The physics is advancing, the tools are improving, and the black hole, that perfect fusion of the most classical and the most quantum, the most massive and the most compact, the most violent and the most silent thing in the universe, is still giving up its secrets slowly, one observation at a time. That is reason enough to keep watching. It is, in every sense, worth watching. The universe rewards the patient.